Oh, here we go. So DNSSec, we'll talk about it a little bit here. Let me get this to resize correctly. All right. So the objective is to verify that your data you receive as a server from another server comes from a genuine trusted source and hasn't been altered. So it started in '97 and continued on there with a lot of changes. The next record was the first authenticated denial, and then you had a delegated signer record, which lets you delegate to child zones. So it continued to develop in 2004 and 2005. As it kept on changing. And so here's the process of signing the records of a DNS zone. You have a resource record like an A record. So you can sign something, and then you hash it with a hash function, and then you sign it with something like RSA or digital signature algorithm or elliptic curve cryptography. Then you have to generate a key pair and use public key cryptography to sign it. So it's not that different than what HTTPS does. And we'll talk about this next semester if we have the cryptography class. It's still not quite clear what classes we're going to have next semester. Anyway, one big issue is the man-in-the-middle attack, which is true of most problems of most public key authority. Public key cryptography suffers from this. If the attacker generates false key pairs, then the victim connects to them and has false keys claiming to be somebody, and it connects to the server and has false keys claiming to be the client, and so it can fool everybody. The only way to prevent a man-in-the-middle attack is to have a trusted third party that tells you if the server you're talking to is really the right server, and in DNSSec, that is the root of DNS you trust. So you have a hierarchical chain of trust. Up at the root, you have a public-private key pair, and you sign the next level down, like top-level domains, and they sign the individual companies, like ccsf.edu, and you have a chain of trust back to the root. So if the root is not tampered with, then it is possible to verify with great confidence that everybody is correctly identified. So the delegation signer record is the links in this chain of trust. All right, and there's a diagram of how it's built, but I think all we need here is the main idea. And I mentioned authenticated denial of existence. This is very strange. So what you do is you sort all your domain names in alphabetical order, and then you make a record to say that there is nothing between these two. So if I have a.example.com and c.example.com, I add a record which says there'll be nothing in between there. So that proves there's no b.example.com. That's how it works. All right. That's an Dnssec record to prove that. All right. The problem is this means it's easy to find all the domains in a zone. There's Dnssec will make it easy to see what names are not used and therefore what names are used, and that is considered a security flaw. People often define special names in DNS and they don't want you to find them. For example, unfortunately, Cloudflare does this. If you define a Cloudflare DNS record, it's protected by default by Cloudflare's proxying. But if you're going to use non-HTTP protocols to connect to it, you can't run those through Cloudflare. So you have to have a second domain that points directly to your server, and that's a secret because people can take down your server by attacking it. So it's fairly common that there is a public domain name that you don't want people to find, and this is considered a flaw. And Dnssec 3 fixes that by hashing and salting the owner name. So you hash the domain names, then you sort them, then you mark what's in between, and knowledge of that does not make it possible to deduce all the domain names. But as you can see, it's getting pretty complicated. All right. All right, there we can see that at the mill, CIA.mil had it when I tried this. You could see these records. The Dnssec 3 was there in CIA.mil. I don't know how many other people are actually bothering to use it, but it's there. So there are also some weaknesses in DNSSec. An attacker in the middle can publicly forge responses to the end user because the end user's browser does not enforce DNSSec, so it doesn't protect you from a liar that is closer to you. It only protects the server from getting false records from other servers. But it doesn't protect you, so that's annoying. And it doesn't protect the glue records. We mentioned these before. Every domain has to have a hard-coded IP address of its authoritative server in the top-level domain, like .com or .net. And those things are not protected by DNSSEC. And when you change things, you might have to change those cryptographic keys. Things can expire, and they don't propagate down the tree, so it's hard to update them. And Dnssec 3 can have a problem here where it can block resolution of a domain. So, there are a lot of obscure problems with it. If you move to a new hosting provider, then the old IP address can continue until the signatures expire because there's no way to push an urgent update to the DNS tree. All there is when you send out a DNS record, you include an expiration time, and the only way to change it is to wait for that expiration time to expire. So that's a fundamental flaw in DNS. All right. And if you can crack the hashes, then you can use Dnssec 3 to determine all the valid domains again. And cracking hashes is difficult but not impossible. It happens all the time with password hashes. All right. There's another flaw with the authentic AD record. And as I mentioned before, it makes the zone files very big and it makes the DNS replies very big. So it creates a lot more traffic. And that means you can use it as a multiplication of traffic attack. And it costs a lot more CPU time on all the servers calculating all these cryptographic records and distributing them. That's why people don't like it much. So therefore, there are other protocols added to DNS to improve it. And one that was popular for a while, although I think it's now fallen out of popularity, was DNS Curve. The goal here was to protect the privacy of the end user. So the end user is not using decrypted, unencrypted DNS traffic all the time, exposing their internet browsing. So they added this thing called DNS Curve, which would then encrypt your DNS traffic locally. And a lot of people tried to deploy this, but it wasn't very popular. And the thing which actually became popular, even though you could argue it makes no sense, is DOE. DNS over HTTPS. This is now built into Firefox by default. So this is what happens. You use HTTPS to connect to your DNS server, and now your DNS requests and responses are encrypted over HTTPS. It works, but it is illogical and very much offends the IETF because DNS is supposed to be a low-level protocol around layer 4 or 5 of the 7-layer OSI model. But HTTPS is at layer 7. So logically, if you turn on your computer and your computer doesn't know anything, to create an HTTPS connection, it has to resolve a DNS name. So it has to do that without using DOE. It has to do that using old unencrypted DNS to find the server, then make the HTTPS connection, then future DNS requests can be encrypted. So it is fundamentally sort of illogical. It's putting a low-level protocol over a high-level protocol, but in practice, this one seems to win in the marketplace. And this is quite common, that the end result is a strange, mixed-up mess, which just becomes popular, and the pure engineering solution is not the one that wins. Anyway, that seems to be the modern solution for encrypting DNS traffic. Anyway, that's all I wanted to say about Chapter 6.